afternoon, everybody. I'm very happy to be here in Bologna today and to see such a full room. Really warms my heart. I hope I'm not going to disappoint any of you. Well, at least not most of you. Anyway, as Alessandro said, my name is Pietro Mascolo, and today I'm going to be talking about graph machine learning in general with a few examples. I do have a blog that Alessandro mentioned. I don't really update it very often, so don't be too disappointed if you visit it. Anyway, let's move on. You can find the slides and the code for this talk at that URL. It's just a GitHub repository. Today, I'm going to walk through a few things with you. I'm going to give you a very high-level introduction about myself and what I do. I'm going to talk a little bit about graphs in general, what they are, how can be used, and how they can be useful for machine learning. And then we'll talk a bit more about how we can use them specifically using Python, first with NetworkX, and then building more complex and sophisticated models using PyTorch Geometric. And we walk through a real-world example-ish. I was hoping to work with a more concrete example, but I have to work on my laptop, which is old. So I did my best. A couple of words about me. My name is Pietro, as you've been repeated a few times already. I'm also using emoji as the previous Pietro to present myself and my history. I have quite a few countries in my flags. I was originally born in Brazil, but I grew up in Italy, actually just in Modena, 30 kilometers away from here. Now I'm based in Ireland, and I ended up marrying an Indian woman. I'm a husband to Pallavi, and I'm a father to Arav, who are the love of my life and the source of most of my gray hair. I have been working as a data scientist and an AI engineer for the last 15-ish years across many different domains and many different companies, mostly in Ireland, but I have a past here in Italy as that as well, which was very interesting. A lot of my former colleagues are actually here with us today at the conference, some of them in the room. I'm always happy to see them again. I am passionate about a lot of things, mostly technology related, but I also have lots of very expensive hobbies, which include photography, ham radio, hiking, and martial arts. And if you're looking to get in touch with me after this conference, you can probably find me on most social media with my handle at IZ4VV, which is incidentally my operator name as a ham radio operator. So what are graphs? I'm sure that some of you might have encountered them. Actually, how many of you have worked with graphs? Oh, great. More than zero. It's considerably more than zero. I'm very happy about that. So I'm going to skip over very quickly about the introduction. I don't want to leave it completely off because some people might not be as familiar as you. But graphs in a very high-level representation and description are essentially a way to describe relations between entities and a collection of entities. The relations are called edges or links, and the entities are called nodes. And these can be many things. We'll be mostly looking at homogeneous graphs in which you have nodes and entity and connections and edges that are of the same type, but you can also work with more complex heterogeneous graphs that have many different types of nodes and edges interacting with each other. And one thing that we need to understand is that graphs are everywhere. Even things that we don't think of as graph could be potentially represented as graph. And I have a couple of examples here. Actually, one of the very first problems that was solved using a graph is the famous problem of the 7 bridges of Königsberg, which was a riddle. We were talking about Euler, so we're going back a few centuries. And the enigma was essentially, is it possible to cross all the 7 bridges in the city of Königsberg without crossing the same path twice and crossing each bridge exactly once? And if you just look at the map, you might end up working many possibilities. But if you simplify the map and just look at the graph, it's fairly easy to say that the answer is no. And that's why we use graph. They're a simplification of reality. Some examples include social networks. It's probably the most illustrious example that we can think of, where people are nodes and all the friendships and connections are represented by the edges. Or we can go to more complex graphs, for example, fraud detection rings, or e-commerce, where you have multiple types of nodes and edges interacting, where you can have, for example, nodes that represent customers and edges that represent orders or that represent complaints, or and other nodes that could represent, for example, suppliers or other entities. And lately, there's also a lot of use of graphs also in biology for protein analysis and protein discovery. But there are also plenty of other data structures that we don't usually think of as graphs, but could be represented as such. Like, for example, images. Like, if you really wanted to, you could think of an image as a graph where each pixel is a node, and each connection is each neighbor pixel to the one you're looking at. That's a possibility. Probably not the most efficient representation, but it works. Text could be looked as graphs, where you have a direct connection between each subsequent word. As I mentioned, proteins or molecular structures could be looked as graphs, and there's actually lots of work that we're not going to be touching upon too closely, but it's quite interesting in terms of protein discovery or, for example, predicting the toxicity of a compound. And then, of course, social networks and how people interact with each other. This is from a very typical toy data set, the karate club data set, which is close to my heart because I've been practicing karate for coming on 30 years now, which represents how people interact with each other. And you can predict how communities form based on the interactions. Okay, I think we can go away with the introduction and we can start talking a bit more about how do we use graphs in machine learning, not just at a high level. So traditional machine learning generally struggles with some sort of relationship-heavy data, and it tends to ignore a lot of the features that we could use. Graphs are great because they allow us to understand not just the structure of the data, but also relationship among entities. They can help us working on problems like node classification or link prediction, for example. Is it possible that a connection will form between a potential client and one of our suppliers? Is it possible that a certain transaction is fraudulent or not? Or how likely is it? Or graph classification, like predicting the type of a molecule and so on and so forth. And in general, these are data representations that are very well suited to represent and analyze very complex relationships patterns. And there's plenty of different types of problems that you can solve or at least analyze and work on using graphs. As I mentioned a couple here in node classification is in determining whether a person is trying to commit fraud or not, or graph classification, for example, trying to understand what type of a molecule you're looking at just based on how the atoms are arranged. There are also plenty of regression problems where you're trying to understand the numerical value that's associated with a node or an edge or even a full graph, like, for example, a molecule's toxicity. And then there's all sorts of more complex problems that can start ranging all the way into Gen AI, into generating new graphs. But we're not going to go too deep in that. Graphs with NetworkX. So NetworkX is a library, Python, of course, this being a Python conference, and it's used to represent and analyze graphs. I'm not going to go too deep into this, but there's plenty of things you could do to analyze your graph just by using this library. For example, here, we're generating a very simple graph. We're adding a few nodes and with connections between them, in this case, just 4 people, and the way they interact with each other. And we can easily visualize the graph. Sometimes just the visualization actually helps a lot in understanding the patterns and the structure of the interactions. Or we can start analyzing a bit more in detail some properties of the graph. So what kind of nodes do we have? How many edges do we have? What is the degree of each node? Or which is the node that has the highest degree? And by degree, we mean the number of connections that the node has, either inbound, outbound, or total. We can also try to find what is the shortest connection between 2 nodes. This is especially useful in very complex graphs, and it's essentially what most of your GPS navigators would do, trying to find a route from place A to place B. How do we represent the graphs, though? That's a very big problem in machine learning, because what we usually do is use something like this. This is called an adjacency matrix, and what you're seeing here is the graph of interpersonal connections of the characters in the Othello by Shakespeare. And it's not obvious, but these 2 matrices represent the same exact graph. The problem here is that when you use this representation, the order of your nodes matters a lot. So as is, this sort of representation like this doesn't really work for us because we want something that is not affected by permutating the nodes. Like we want something that's as stable as possible for mathematical work, of course. So there are ways to obtain what we call a permutation invariant representation. And one of the simplest one is just by using what's called an adjacency matrix, which describes how each node is connected to every other node in the graph. And NetworkX and a lot of other network tools allow us to do exactly that. In this simple example here, we have an adjacency list, which represents each node. There's a row for each of the nodes in the graph. The first element in the list is the node itself, and the subsequent elements represent the connection that that node has with other nodes. It's the most concise way to represent a graph, which could become very big. Sometimes we're talking about millions or billions of nodes, so concisiveness is a good thing. And I didn't mention before, but each node and each edge could also have additional properties associated to them, and they usually do. And that's usually what allows us to make predictions or make inference about the type of graph and the type of network that we have in front of us. Okay, we just had a quick look at how to represent the graphs, but how do we use them in an actual problem? How do we use them in a mathematical sense and in a programmatic sense to solve problems? There are many simpler types of algorithm, but for today we're going to focus on what is called a graph neural network. A graph neural network is exactly what it sounds. So it's a neural network that instead of acting on tabular data or on sequences or on images, it acts on a graph. And the way such a graph learns is it learns a representation, an embedding for each of the nodes based on the node's attributes and its neighbor's attributes. And it generates an embedding that can be used for future inferences, or it could be used in a subsequent neural network or other model for predicting something or for classification or what have you. And we're going to focus specifically on just one type of architecture for graph neural networks, which is the graph convolutional network. If you're familiar with a regular conventional convolutional network, the way a graph convolutional network works is pretty similar. It's just that instead of looking at the neighboring pixels of a single pixel, you're looking at all the neighbors of a node with each convolution. That's a very simple analogy there. And the mechanism through which each node learns through its neighbors is called message passing, which is actually very similar to its convolutional analog. So the node gathers messages from its neighbors, so the value of the attributes and features of the neighbors, or the edges that connect them. These are aggregated together, and then through a small neural network, the node embedding is updated. I promise this is the only slide with maths. So the mechanism is probably very familiar to you if you have worked with neural networks. You have an aggregation of signals with a certain weight matrix that is learnable. And you have a nonlinearity, or sigma, which is usually ReLU, but could be any type of nonlinearity. Some work, some don't. And that's what you get at the next step. You compound these steps a few times, and you have a graph convolutional network. Very simple. Kind of. Convolutional networks for graphs are only one of many possible architectures. There are some that have a very similar analog in the conventional space, if the slide progresses. For example, we have graph attention networks, which, as you can imagine, introduce an attention layer, attention type layer. It's not exactly the same thing, but it's very analogous to what you would see in a neural network with an attention layer. You have graph sage, which is actually a fairly interesting type of architecture, which introduces not just aggregation. It could also, in some cases, include an attention layer itself, but it can generalize to more advanced types of pooling and even using LSTM layers to learn over time from each neighbor of each node. And then you have also isomorphism networks, which are trying to learn the structure of the whole graph at different scales using perceptrons, really. And they can be used to detect changes over time in a graph, which could be useful, for example, if you're running some sort of problems in the space of fraud detection, because like fraudsters tend to evolve in terms of their behavior. So in a nutshell, what GNNs do is they learn all embeddings. They have a mechanism called message passing, and that allows each node to learn from its neighbors over multiple paths. And they can be useful for all sorts of tasks. Let's have a look then at a very quick implementation. I try to keep it as simple as possible, and I also have a very short benchmark later on to show you how these networks compare with more regular techniques. I'll be using a library called PyTorch Geometric. Has anyone here ever used it? Ooh, three hands? Okay, 4 hands. Okay, not that many. So as you can imagine from the name, PyTorch Geometric is part of the PyTorch ecosystem. And in many ways, it's an extension over PyTorch, just including new architectures that can be used on graph. As you've probably seen with most other architecture, this also inherits from module. And we have a new type of layer in this case, and we actually have many types of layers, but we're going to use the GCNConv, which is a graph convolutional network layer, sorry, this is a layer. And we're going to use 2 layers. One thing that you will see that tends to be quite different between conventional networks and graph networks is that graph networks tend to be quite shallow. And the main reason is because, well, you're essentially running a small neural network on each node of a graph. Imagine having 1 billion nodes. Each of those has a small neural network running on top of it. It gets inefficient really fast. Anyway, back to us. So it's a very conventional network in our case. We have 2 convolutional layers. We apply one, we add a nonlinearity, ReLU. We apply the second, and we have a softmax. Very simple, very conventional. Training, again, PyTorch makes things simple for us. So we have an optimizer, we have a loss. We just iterate over the data set multiple times, and we update our optimizer based on the loss. The evaluation is also very simple. We set the model to evaluation mode, collect a prediction, and compare them with the original data. Nothing weird, nothing esoteric about this. Let's have a look at how something like this behaves on a real scenario. So I'm going to be using a graph data set, which is called Cora. It's a citation network. I'll give you a few numbers about it in a second. It essentially represents multiple papers. We're talking about 3,000 papers, 2,700 papers that are connected with each other via citations. The number of connections is about 5,400. And all of these papers are part of one of 7 categories, depending on the type of publication. The task is trying to predict what category each paper belongs to. And each node, so each paper, also contains a bag of words set of features, about 1,400 features. Initially, I wanted to actually have a live coding session about this, because it's, if you look at the numbers, we're not talking about a huge amount of data. In the end, I decided not to, and you'll see why in a second. So the way the labels are distributed, yeah, as I mentioned, there are actually, there's a mistake here. It should be 70 topics, not 7. And each node represented by a paper. Each paper is represented by a node. Sorry about that. So the main reason why I don't have a live coding session, the code is with the repository. So if you want to have a look at it and run it, please go ahead. But I'm not running it here because when I did that first time, the gradient boosting classifier took a little bit longer than I would have liked. It took almost 4 hours. And that was on a more powerful laptop than this, so I'm not even going to try here. Whereas the graph network actually took less than 30 seconds. So good start. And then when we look at the metrics, the graph network actually did a lot better. by a considerable margin. And just for to give you some numbers here, I used a gradient boosting classifier from scikit-learn, nothing too fancy. I gave it 100 estimators because I wanted to be a bit thorough. So I wasn't trying to bias the ground towards the convolutional network, which is exactly what you've seen earlier in the code. Exactly that. And as you can see from the results, the graph network worked a lot better, right? And the main reason is the fact that the gradient boosting didn't take into account how each paper cited each other. It was just using the backwards content of the papers, which is considerably better than random guessing, but it's still way worse than what the convolutional network could do. So I will try to be a bit quick here about a few things. We're coming to the end. So one major positive, or major pros of graph neural network is the fact that they capture not just the data and the tabular representation of values, but also relationship. And I have used these successfully in a lot of situations in which relationships are key, like for example, fraud detection, or I use them quite a lot in the clinical domain, try to understand what patterns will emerge over time for disease prediction and for risk prediction. And most data in the real world is relational after all. So like having a good understanding of how relations impact the final outcome sometimes is very important. It can be used, and I have used it in building recommender systems, which can be very helpful in understanding not just the direct behavior and transactional behavior of the users, but also how they aggregate together, what kind of communities exist, what kind of similarities you have. Excuse me. And as I mentioned, it's fairly used in molecular biology as well these days. Okay, we're coming to the end. I'm actually going to open it up for questions, so that I hope there are a few.
Okay. Sorry. Yes, there are coming right now. Okay. So why Cora dataset edges are undirected? Paper X cites paper Y doesn't look like a symmetric relation.
Yeah. Well, in this case, the edges are in fact directed, not undirected. It is the type of edge is paper cites paper, so it starts from a source and it ends up in a destination.
Okay. And another one is, how can you handle horizontal data scaling with graph data?
Ooh, this is interesting. Actually, this is one of the major issues that you have building graph data and representing it. There are a few tools that allow you to do that. I have to say one of the major disadvantages of graph data and graph databases in general tends to be cost. There are some tools that are insanely good, insanely fast, and they can scale up really well. When I was working in a previous company, we actually had a production database, graph database, that we were using to run analysis and train machine learning model, and it scaled easily to well over 1 billion nodes and God knows how many billion edges. And it was still performing really well. The main issue there, as I mentioned, is finding the right tool, the right representation, getting the right type of schema for representing your data is key. Similarly to a relational database, you can scale a lot better if you represent your data in a proper way. Yeah, that would be my take on it.
Okay. Another one, how large can the dataset be for a GCN, and how do you deal with supernodes?
Okay. I never had to directly deal with supernodes, so we can, like, if you were curious about that, we can have a chat offline, perhaps. In terms of how large the dataset can be, it's really limited by your time and compute. It's very similar to what you would find using conventional networks. In my case, running it on my laptop for 4 hours was fine. If it had run for a month on my laptop, it would not have been fine. But in some cases, and depending on your goal and type of model you're building, a few days, few weeks even, so you could probably scale to up to a few gigabytes or terabytes even. Depends on your hardware.
Okay. Another one. Do you do any data augmentation with training with GCN? Like, for example, shuffling nodes around similarly to how you may shift, rotate an image in a regular CNN?
You can do something like that. Well, there's definitely a lot of data pre-processing that goes into it, mostly about standardization of the data. Clearly, GCN being a type of neural network benefits from having some type of standard representation of the data. Not as much as some other models, but still might be beneficial. In terms of data augmentation, it tends to be not as important, at least not in my experience. There are techniques, but to be honest, over the last 10 years, I probably used them once. So I can't even say I'm an expert at that because I used them once.
So another one is, can you combine several GCN in an ensemble method?
Sure.
Why not?
Definitely.
You can assemble anything.
I'm actually a big fan of ensembling different models together, especially if they are all looking at different types of features and different type of patterns. You should be careful to make sure that you're not ensembling two things that are looking at the same type of features, though, because it's a bit redundant.
Okay, another one. We have plenty of time for questions. Thank you for you ended
I tried
earlier.
to power through it.
I don't get the intuition behind graphs neural network. With normal neural networks, we are learning vector embeddings when we have each point in n-dimensional space and we can compare. What's the situation in graphs?
Well, the analogous here is that instead of learning data points embeddings, we're learning node embeddings or graph embeddings, or even edges embedding. So you're trying to represent in a concise way that still carries lots of information, either the entities you're trying to model, how they're connected to each other, or the whole network. I think it's a very similar type of result in the end. Then you can use those embeddings to generate more insights as to how your entities are behaving.
Okay, other questions are coming, so thank you. What are the computational or infrastructure considerations when you're scaling GNNs to millions of nodes and edges in a real-world banking scenario? Context, sorry. That was
a real-world banking scenario?
Real-world banking context.
Banking context, okay.
The wording. Yes.
Well, the considerations would be the same that you have in other analogous situations with regular conventional models. So data representation tends to be key. You want to have fast retrieval times, fast operation times. Aside from that, some tools are beneficial in terms of retrieving the data and representing the data for optimizing for how relationships are represented. I mentioned that there are some graph databases. I can give a couple of names. They're publicly available paid products. So some of these would be, like, for example, Neo4j, which is probably one of the oldest players in the market. We had lots of success in the past using Tiger Graph, which is a little less user-friendly, but considerably faster and considerably more expensive as well. And that actually really allowed us to perform very deep analytics on 1 billion+ nodes very quickly. So we're talking retrieving hundreds of thousands of nodes in less than a couple of minutes through complex relationships analysis.
Yeah, there is a question related to that. How come the graph-based model learns so much faster than the gradient boost classifier? What's the core point behind that?
Well, the main point is that gradient boosting is a great type of model, family of algorithm, but it's not the most efficient I know. So the problem with gradient boosting is that, especially if you give it a lot of trees, it learns sequentially, right? Whereas graph neural network, especially if you have a decent CPU, ideally the GPU, it's just matrix operation, so it's very quick. And the optimization for gradient boosting in particular is way far from being as fast. So that's, in this case, it's mostly because of the algorithm. I could have chosen something like random forest, which could be easily parallelized, and it would have been a lot faster, but it also tends to be not as good in terms of tabular data prediction in most cases that I've seen. So I tried to give the challenger model a bit more of an edge in this case, but still.
Okay, they are keep coming. Okay, great. But we have you are over time, so last one.
Okay.
Does it make sense to apply GNN on embeddings derived from another network? For example, a convolutional neural network or any other encoder for images?
This is a deep question. I don't think I can answer it. I need to think about it for a second. Does it make sense? I would say it depends on how you look at the embeddings and create them. Because here you're looking at node attributes and how they're linked to other nodes. What do these embeddings that you bring in as input represent? Because if they are just node embedding, it might make sense in some ways because it's essentially a rehash of what you've done, or what you would do within the GCN. So you're learning embeddings from the neighbors. Mathematically, in my head, it does make sense. I don't know if it has a physical meaning. I would have to think a little bit more about that.
Yeah, I wonder how you get out the value out of it. How do you build a graph out of the embeddings? So anyway, we are over time. So thank you very much, Pietro.
Thank you. Thank you.